This is the video podcast for Chapter 9, which looks at some recent urban hydrology studies. So the goal of this chapter is to return to the kinds of questions that we were asking in forest hydrology and rangeland hydrology. Instead of thinking at a bigger scale about the impacts of urbanization and the economic effects of those impacts, we just want to come back down to the scale of a plot. And in this case, a plot might be a house or a road, and ask questions like, interception, through-fall, stem flow. But of course, we don't have trees, we have houses, we have roads, so we want to see how this urban infrastructure functions. In the previous podcast, I was talking a lot about urbanization, urban landscapes, as if it's a relatively homogeneous thing, but it's quite different. What you have in a suburban development usually consists of individual standalone homes or maybe duplexes. And then you have lawns and you have gutters and then roads. You might have underground sewers. So there are lots of different individual pieces. And then there's going to be parks. There might be ponds of some kind that are there, schools. You might have some apartment buildings. So there's really just a real patchwork of what's taking place. And that makes it far more complicated to assess than just saying having like a canopy in the tropics. So the idea of this video podcast is to try to find studies, and there aren't that many, but there are a few, that have tried to treat urban areas as if they're just anywhere else and take technologies that we have in hydrology and use them to study the water balance in an urban context. The first case study I want to show you is looking at runoff from rooftops in the UK. This was a study done in Wallingford, and the purpose is just to understand the water balance of rooftops, just like we could think of a rooftop like a canopy. Whether it's to try to hold the water back and not affect downstream flooding, or to make use of that water. There's a variety of possible uses, but just trying to understand the hydrology. So the objective, study the effect of roof shape, slope, and aspect on rainfall runoff, and particularly evaporation and the ratio of evaporation to rainfall. As you can see from the photo, the roofs here are pretty simple. They're just like, V-shaped with two faces. And so in this study, there were 5 individual homes that were looked at with slopes of either 0, 22 degrees, or 52 degrees. And then they were either oriented such that they were south-facing, east-facing, or north-facing. The importance there is that south-facing slopes receive sun because the sun's moving across the sky to the south when you're in a northern area like the UK. And so as the sun's going across, then it's going to be beaming the light that may then create more evaporation, even if it's cloudy. We also have some other measures that are shown here. But really the overall goal is to see what is the ratio of evaporation that takes place on a roof, and how is that influenced by slope and orientation. The methods that were used here, as you can see, there's a funnel on this sloped roof, and notice that this funnel is at a slope too. So that means that water either has to hit it facilitated by wind pushing it in there, or when water is falling down on a sloped surface, then you're just going to catch water into what we can consider the projected area. Like the projected means the horizontal area for that slope. So you have a slope like this, but all that matters is the horizontal space associated with that slope. So that horizontal distance is less than the slope distance. So they use a tipping bucket rain gauge to measure that gross precipitation on the roof. And then you have runoff that's then coming into the gutter. That gutter goes into a barrel, and then they have a water level sensor that's measuring the water levels from which you can get the volume of runoff. Wind direction was measured with a wind vane. And then it's assumed that all of the water that is actually stored in the roof itself, whether it's in shingles or in pockets, porous spaces, is assumed to evaporate away. So evaporation equals gross precipitation minus runoff. Now this is a little bit challenging because if you ask me, the first thing I would expect is that the steeper the slope, the more runoff you get, because a steeper slope means that velocity is faster. So you should be shedding water off at a faster rate than and of course the infiltration is going to be relatively minor, and you'd think that if you can run off faster that you won't evaporate away. But there is a competing process, and that is rainfall itself. So if we look at these roofs, let's see, if we go back, the first three are 22 degrees, and then there's one 50-degree roof. So if we look, let's see, the 50-degree roof is IT. So if we look at the overall amount of rainfall, notice that the amount of rainfall there is 14,000 liters compared to 24 to 45,000 liters for the 22-degree roofs and 55,000 liters for this other house. So it's possible that you have different amount of rainfalls. We don't really know. But what it more is likely here is that the flatter the surface is, the more horizontal, like projected area there is. And so, like, you know, the steeper roof, well, you can't see it here because, well, yeah, right. So you see how the steep roof, it has a big surface area, but that's the three-dimensional surface area. Like that's this line, the length of that line, plus the length of this line times this depth of the roof. Whereas the plan area is if I were to just draw a horizontal line straight across and then multiply that by the depth of the roof. So the difference between plan area, like just if you look top down versus the actual three-dimensional area of that roof, you can see it's dramatically different. I mean, and that difference is what drives the hydrology here, which is quite interesting. So we have substantially lower total amount of rainfall, not because it's receiving less water in terms of what's falling out of the sky, but because it's a smaller area of plan form roof to catch the water. And as a result of that, let's see, so there's less total rainfall. You still have a fair amount of runoff. You can see runoff is actually quite high. There's only a really small amount of evaporation that takes place. And so as a result of that, when you convert all those to millimeters, we can find that 56% of the water that fell on that flat roof evaporated away compared to these other ones that had relatively low. So if we look at the natural site, we have 66% of the water evaporating away. So that's consistent with what I've told you in the past of like 50% of the water in a natural water balance going to evaporation or evapotranspiration. Here there's no transpiration, so it's just evaporation. With a medium slope roof like 22 degrees, you see 13 to 33% evaporation, and for this very steeply sloped roof, almost, you have 56% evaporation. So let's look at the results in terms of what they found. Less sloped roofs receive more rainfall overall, and as a result, they have more total precipitation. And if you hold at the same aspect in terms of sun angle, you get more evaporation. Roofs that are facing the prevailing wind direction will receive more rainfall, but they also will have more evaporation because the wind promotes evaporation. And then south-facing roofs are getting more sunlight, so they have more evaporation. So that's consistent. So the interesting thing in this diagram is through time, if you accumulate the amount of water through the storm, the lower sloped roof accumulates more water than the steeply sloped roof, which is a little bit counterintuitive, but again, it's because getting more rainfall trumps the speed with which the steeper slope can shed water. Here are some more results. In the left plot, you can see time over months, and so you see the seasonal pattern of peak rainfall taking place in the fall and to a lesser extent in the winter, and then less rainfall in the summer. If we look at the ratio of runoff to rainfall, which is the lines, we can see that there's a greater fraction of rainfall going to runoff during the winter months, and then there's more evaporation taking place during the summer. And there's a lot of fluctuations that are in there. For any given amount of rainfall, you can see that the steep slope roof is producing more runoff. In order for that to happen, though, that's assuming that you're getting the same amount of rainfall. So a key difference from this slide here is that they in fact receive different amounts of rainfall. But for any given level, the steeper slope does win out and it sheds off more water. So this is what's a little bit confusing, is we have conflicting processes. One process is driven by the plan area of the roof. The bigger the plan area, which is associated with a gentler roof, the more total water you receive. But less of that water should be going to runoff because it's flatter, so it has more time for evaporation. And so that's what these two different plots are showing. Okay, now let's shift from roofs to the ground. And if we look at the paved ground, it's be pretty interesting to ask how much water is infiltrating. So under a normal condition, what I told you before is about 10 to 30% of the rainfall should infiltrate. So what happens when you have an impervious paved surface? And of course, just how impervious is impervious when we say that. So the objective, investigate the processes of road runoff and rain infiltration for some different road surfaces. Again, this study was done by the same team in Wallingford, UK. Here's a typical soil profile. The top 60 centimeters being just what they call brown earth. Below that, yellowish brown sandy clay for another 30 centimeters, and then mixing in some gravel below that. Here are two parking lots, so relatively flat asphalt surfaces. There's 8 centimeters of asphalt underlain by either 50 or 40 centimeters of ground crushed oolitic limestone. And then below that, you have the regular soil profile. Here are some newer surfaces. One shows with pavers. And so these block pavers, like bricks that are there, allows for some infiltration in between those. The pavers are 8 centimeters high, and then there's some weak concrete below that for about 40 centimeters. And then below that, the regular soil. And then here's a road surface away from parking lots, similar to the other parking lots where you have 9 centimeters of asphalt underlain by about 40 centimeters of limestone. The methods here involve measuring rainfall and groundwater level. So that's probably done with a piezometer, and rainfall with a tipping bucket gauge, but measured on a weekly basis. And then soil moisture profiles through and below each surface were measured weekly in 10 centimeter intervals down to 3 meters using something called a Neutron Probe. If you've taken a soil physics class or a field methods and hydrology class, you've probably come across a Neutron Probe. It's a device that you put on top of a well, and that well, just a shallow well, what we call an access tube. It's like 2-inch diameter tubing that goes down, usually made out of plastic, and then you lower on a cableway. You just hand crank down. You lower down this device. The device has two parts. One is a neutron emitter. So it uses, this is a radioactive device. It's emitting neutrons. A neutron, remember, that's like the nucleus of an atom, and that is about the same size as a hydrogen atom, because hydrogens consist of 1 neutron and 1 proton, where the neutron is a lot bigger than the proton. And so if you think of this as pool table balls, you have balls being emitted here by the neutron. And if you think about something moving very fast, because these are emitted very fast, then when an object that's a particular size hits another object that's the same size, they both slow down dramatically. If it hits something very, very tiny, it's just going to blast through and keep going. Or if it hits something that's dramatically bigger, it's going to reflect off, remaining at about the same speed. So it's only when two things have about the same size but that they cancel out each other's momentum. And so these fast neutrons are emitted, and then the more water there is in the soil around it, the more likely it is to get slowed down. And then the detector looks for what are called these slow neutrons. So that's the general idea. You just lower this down, you pause at a location, and then you get a count over a period of time. And that count can be calibrated to yield a water moisture content if you go out and collect a core somewhere else and see how much water is actually there. You can make a regression equation using a scatter plot between neutron emissions and detections and the actual moisture. So a neutron probe is used to measure the moisture abundance at different levels, and then you come back through time and you see how the moisture is changing through the depth. So this shows the overall balance where the rainfall is given at these 4 different sites, and you can see it's the same amount of rainfall. And then the gain here is the amount of infiltrated water in millimeters and in percent. And it's really the percent that matters. So if we look at this RS4, that's the road surface 4. So that's off, kind of in a more regular context. But you can see that that's getting about 6.3% runoff. And then you can see these other sites anywhere from 6 to 9%. I'm sorry, not runoff. This is infiltration. 6 to 9% infiltration in the car parks. So it doesn't make much of a difference, and actually being underlain by that light concrete seems to be ruining the benefit that you would get from having pavers. But overall, we're seeing 6 to 9% infiltration, which is a really low amount because it should be more in the 10 to 30% range when you have a pervious surface. So it really does make a difference, and it's really nice to have this mechanistic, quantified look at it rather than just the concepts I presented in the previous chapters. This shows the response through time. The bars on the bottom are the rainfall amounts, and then the lines show what's happening, the overall soil moisture in the different sites. If you look at grass, the soil under grass has a very large amount of water, total water in the 0 to 40 centimeter layer, has a lot of water during those rain events, but then it seems to drop off as the rain drops. You get another storm and it heads up again with these storms. So it does fluctuate quite a bit depending on the rainfall. On the other hand, the road, asphalt, and block situations, surfaces have relatively constant amounts of moisture, and they just stay wet because they're going to get wet. They're going to get the moisture because there's a small amount of infiltration going through, but they have no way to really give up that moisture once it's there, and so it stays fairly constant with minor fluctuations during those storms. Okay, the next thing I want to do is take a step back and look at some analysis that was done using computer simulations to try to assess potential benefits of promoting more infiltration. So in places like California, Australia, and Israel, which are semi-arid urban areas, we tend to be hurting the recharge to the aquifers. These are cities where, these are states and countries where cities rely very heavily on groundwater. Here in Davis, California, at the moment, we're like 100% groundwater dependent. That helps in drought years where there's no surface water, but on the other hand, over a long period of time, you can really diminish the groundwater and hurt the aquifer. So the question here is, could we do things to promote infiltration, and what kind of benefit would that yield? If we look at an individual house, houses do have a fair amount of mindful hydrology taking place here in this kind of suburban development. Unlike the case in Wallingford, what you can see here is that there are small lawns all the way around the house. And what typically happens is that the water from the gutters stops at the lawn, and then you might have a perforated pipe that's going through, or it might just stop and you get sheet wash over the lawn. And so in this sense, the lawns act as what we could call infiltration strips, which are defined here. And so those infiltration strips do promote infiltration compared to just having relatively impervious concrete. An even better technology would be to have a trench, so collect water from multiple houses and then dig a trench and have the water dissipate into that trench. So it's essentially you're creating an underground storage tank, but instead of being totally empty, it's like a porous material made out of gravel and stone. And the hope is that the water that's filling that trench will then infiltrate into the ground and recharge the groundwater aquifer. So in this case, a relatively simple modeling approach was used. We start with rainfall intensity through time. We call that a hydrograph. I can't remember if we've gone over that or not. So you take the hydrograph and then you decide, are you over a pervious, like naturalized land, maybe a lawn or something like that, or are you over an impervious surface? If you're over a pervious surface, then we're going to subtract water out of rainfall for water that we could say is lost to infiltration, depression, storage, and evaporation. For the impervious surface, we're just going to have depression storage. So where you have dips in the cement, then water can be stored there. And you're also going to have some evaporation. So each of these words here, phrases, is basically associated with an equation or a constant that's going to define that process. So I'm not going to go into those equations now. We'll do that much later in the quarter. So after you subtract out those water, then from the initial rainfall, you have what's left, like a residual, which sometimes we've called that rainfall excess. Here they're calling it effective rainfall, but it essentially is the runoff. It's the water that comes out of that plot, and then you have to move that water as overland flow, ultimately producing a discharge hydrograph. All the things I've just mentioned are done in three components: a roof model that calculates evaporation and moves water through the gutter to the land, a land model that again calculates evaporation and calculates infiltration and then moves water to the outlet, and then they added a new model where they would then modify the land surface with different features such as infiltration strips or trenches. The model that they have has numerous assumptions, and I'm just going to let you look at them. Of course, all models have assumptions, and they're really just simplifying tools that help us be able to make it a tractable problem. So the results are shown here for two different size storms. Annual rainfall of 491 millimeters in that year, or almost, well, pretty much double that amount, almost like 968 millimeters. So the bars on the left are for the lower rainfall amount, and the bars on the right for higher. I've gone over many times now the fact that when you have more rain, you can simply overwhelm storage capacity, and so you tend to see a lower percentage of infiltration or evaporation or whatever it is, and so you can see that here is a small difference between the two. So I don't think that's particularly interesting. The main thing is to see what's the effect between a regular urban neighborhood versus if you add infiltration trenches or infiltration strips. It's interesting that in both cases, you can more than double the amount of infiltration, but infiltration trenches don't make it particularly big difference compared to strips. And I think the main thing is that because they're still porous, they're porous, but they aren't like big holes, so they don't have enough storage capacity, and so the infiltration strips are doing well. There's way more infiltration strips than you can have infiltration trenches. But you can see a significant difference between the two. Finally, we can just think about an overall array of stormwater best management practices. Like, given the information here and the consequences we've seen in the previous two chapters, what are some things that can be done to help abate the problem? This is really an engineer's approach, because obviously we're not going to reduce the amount of urbanization on the landscape. Well, for one thing, we can collect more water at the roof by have a barrel at each house, and then you get that volume of a barrel. That's going to have a disproportionate benefit for small storms compared to large ones, but it's a place. We can promote infiltration by having gravel and paver surfaces rather than having impervious concrete. We can have the water go to channels that are not concrete lined but are naturally lined so that there can be transmission losses in the channel. And then you can have wetlands or basins that will receive that water and provide storage capacity through a storm, which abates the flood peaks. If we look at a block of West Davis here where I live, what you can see is a number of these features. Of course, each individual house has essentially infiltration strips. There are some trees here, so that's going to catch water and transpire it away or evaporate off of the intercepted water. Notice that there are two ponds here. This is Stone Gate. It's not looking too healthy. And then there's this other one that's here. And so these two are going to be receiving stormwater runoff from the homes that are around it, and therefore not sending it to the main waterways. You could also see there's a field here that could be storing a lot of water. And then around the whole north of Davis is a channel, like a flood channel that collects a lot of water and helps to prevent overflow. So there are a variety of things that are going on overall in our community to try to help offset the urbanization effect itself.